sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. So this defines our change of variable. So it defines our original variables x, y, z in terms of the new variables rho, theta, and phi. So we'd like to compute the Jacobian x, y, z with respect to rho, theta, and phi. That's going to be the determinant of this matrix. So we're going to have dx, d rho, dy, d rho, dz, d rho, dx, d theta, dy, d theta, dz, d theta, dx, d phi, dy, d phi, dz, d phi. So we need to compute all of these. Fortunately, in this example, not very hard, just long. So we can fill in what these are. So dx, d rho, that's sine phi cosine theta. Dx d theta, it's going to be minus rho sine phi sine theta. Oh, need more room. And d phi, that's rho cosine phi cosine theta. And so then we'll fill in the rest of these. So that's sine phi sine theta, rho sine phi cosine theta, rho cosine phi sine theta. And finally, z, we get cosine phi, 0, because z does not depend on theta. And then we get minus rho sine phi. So we have to compute the determinant of this 3 by 3 matrix. All right. Now, I'm not going to remember that one rule that you've mentioned a couple times, so I'm just going to do it the way I feel like. So we're going to take this cosine phi times the determinant of this matrix plus this minus rho sine phi times the determinant of this matrix. Because in each case, whatever element we're taking down here, we're deleting the row and column that is in, and then taking the rest. So we get cosine phi, and then we get minus rho sine phi sine theta, rho cosine phi sine theta, minus rho squared cosine phi sine phi cosine squared theta. And I actually have two sine thetas here, so I'm just going to combine them. Okay. So that's one part. Minus rho sine phi times the determinant of this mess. So we'll have rho sine squared phi cosine squared theta plus rho sine squared phi sine squared theta.
Okay, really quickly, can we go over the determinant of like a 2 by 2?
So 2 by 2 is this times this minus this times that.
Okay.
Yeah. So I erased it. What I was doing last time. Okay. And here we can do a lot of simplifying because we have our old favorite identity, cosine squared plus sine squared is equal to 1. Because here we have sine squared, here we have a cosine squared, and everything else in it is the same. So we're going to get cosine phi, and then we'll get minus rho sine phi, cosine phi. So all of this condenses, rho squared rather, all of this condenses to that. And then down here we have sine squared phi in both. We have cosine squared and sine squared theta, and everything else is the same. So now we're going to have minus rho sine phi rho sine squared phi. Okay. Well, now here we have a sine squared phi, and here we have a cosine squared phi. Everything else in these factors is the same. What's left over is a rho squared sine phi, so we get minus rho sine squared phi, and that's, I did it again, didn't I? Rho squared sine phi. We take the absolute value, so that gets rid of a minus. So by using this identity, sine squared plus cosine squared, a couple of times, we get the factor from spherical coordinates that we expect. All right. So whatever change of variables you have, once you express the original variables in terms of the new ones, compute all the partial derivatives, take determinant of the matrix that results, which is a nice process in 2 variables. It gets pretty ugly in 3 variables. Then you're all set. That reminds me, let's see, what do I do to you on the test? Okay, number 9 is a 2 variable transformation. Number 10 is a 3 variable transformation. Although some changes of variables are not really all that complicated. For example, let's suppose that you have something simpler like this, where each of x, y, and z depend on not all of the new variables, but only one of them. For example, even in this example we just did, z does not depend on theta, which causes 0 here, which basically cut out 1/3 of the work than if we had a full matrix of all non-zero derivatives. Suppose you have something like this. X is, let's call it G1 of u. Y is G2 of v. Z is G3 of w. So we're changing 3 variables to 3 variables, but each of the original variables only depends on one of the new ones. So in your Jacobian matrix, it's going to be dx du, dy dv, dz dw, and everything else is 0. So it turns out that the Jacobian of the coordinate change is just a product of these partial derivatives. Okay, so just because you have a case where you're changing 3 variables to 3 variables doesn't mean that you're going to have some terrible ordeal computing a 3x3 determinant. It could work out as nicely as this. So
We hope, right?
everything I mentioned for a reason. I'll put it that way.
Okay.
All right. Oh, but this is a good thing. So, yeah. All right. Okay. Now, how much time? Oh, all right. All right. So what I'd like to do is use the rest of the time to look at some examples, and I haven't forgotten that there are certain examples of problems taken from Stewart that I will write up solutions to. The setup of the integral, we're going to focus just on that and not the actual active integration, which you've all taken 168. You know how to integrate, right? And in a multivariable problem, once you have it all set up, you're just going to be doing a whole lot of it. That's the difference. Actually, a lot of these problems, including the ones on the exam, the integrands themselves are not really all that interesting.